The single phase transformer tap changers, also known as synchronous tap changers. The thyristors can be used as static switches for on-load tap changing of a transformer. These static tap changers have the advantage of fast switching and smooth control. Here we have considered only two secondary windings as shown in this figure. The primary instantaneous voltage is Vp, is given by root 2 times of Vs sine omega t, which we can consider as root 2 times of primary voltage sine omega t. Now the secondary instantaneous voltages we have considered as V1 and V2. Now V1 is equals to root 2 times of V1 sine omega t, and V2 equals to root 2 times of V2 sine omega t. Root 2 times V2 root 2 times of V1. The gating pulses of thyristors can be controlled to vary the load voltage. We have considered the R load here. Two-step control, we have three possible ranges of output voltage. That is, our first range is between 0 and V1. Now the second range is between 0 and V2, and the third range is between V1 and V1 plus V2. For the first control range, that is 0, and between V1, T1 and T2 can be turned off, and T3 and T4 can be turned on with a firing delay of alpha. So when these two thyristors are turned on, the voltage V1 is going to appear across the load V0. This is our V1 waveform at alpha. Turning on the thyristor T3, then this is the positive voltage appears across the load. At alpha equals to pi, T3 turns off since the voltage becomes 0 here and the negative voltage tries to flow. So after pi plus alpha, T4 I am going to turn on. Then this will be the output voltage. Again, this cycle repeats after 2 pi. The control range between 0 and V2. Here I am keeping T3 and T4 in off stage, and I am operating T1 and T2 with an angle alpha. These two are turned off. Then when T1 turns on at an alpha, the V2 is going to appear across the V0 until pi. At pi, the voltage is reversing, so T1 is turned off and T2 turning on at an angle alpha again. Then this is output voltage V0. And this cycle is going to repeat after 2 pi. In both the cases, in first and second, the alpha can be varied between 0 and pi. And in both the cases, the circuit operates like AC voltage regulator or AC voltage controller. In case of first control, RMS load voltage V0 is given by V1 1 by pi, pi minus alpha plus sine 2 alpha by 2 whole to the power of 1 by 2. In control range 2, V0 is given by V2 1 by pi, pi minus alpha plus sine 2 alpha by 2 whole to the power of 1 by 2. For the third control range, that is between V1 and V1 plus V2, we'll turn on T3 at 0. V1 is going to appear across the load. That is 0. Then at alpha, I'm turning on T1. When T1 turns on, the V2 is going to appear across the load. Cathode voltage of T3 will be more than the anode voltage of the T3. Then T3 turns off. The V2 is going to appear across the V0. This will remain until the pi. At pi, the voltage will be reversed for T1. Then T1 turns off and T4 turns on. V1 in reverse is going to appear across the V0. At pi plus alpha, again I'm turning on T2. Then T4 turns off and V2 will appear across the V0. The same cycle is going to repeat after 2 pi. The RMS output voltage of the load V0 is given by V1 square by pi alpha minus sine 2 alpha by 2 plus V1 V2 whole square divided by pi minus alpha plus sine 2 alpha by 2 whole to the power of 1 by 2. So this is regarding the synchronous tap changer or single phase transformer tap changer for two-step control of the R load, which is used for resistive heating loads. With RL loads, the gating circuit of a synchronous tap changer requires a careful design. In control range, that is 0 to V1, we have the output voltage, that is V0, equals to 2 times V1 sine omega t. And the current I0 due to the inductor will be 2 times V1 by Z sine omega t minus theta. Now the Z is given by R square plus omega L square equal to the power of 1 by 2, and the theta is given by tan inverse of omega L by R. Now this is our V0, then the I0, to draw this, this is 2 times V1 by Z or I0. If T1 is turned on at omega t equals to alpha, if that alpha is less than theta, the secondary winding of a transformer would be short circuited because T3 is still conducting and carrying current due to the inductive load. This is the theta. So T1 should turn on when alpha is greater than theta. Similarly, in negative half cycle, T2 should turn on when alpha is greater than pi plus theta. T1 and T2 should turn on when the load current I0 in this case will become equal or greater than 0. Let this be alpha and theta is this range. This is root 2 of V1 plus V2, and this value is root 2 of V1. Here the alpha is more than theta. T1 is triggered, T3 is T4, T2. Now this value is root 2 V1 by Z. This value is root 2 V1 plus V2 by Z. This value is theta. This is alpha from here to here. Conducting angle is given by beta minus theta. So this is the output current I0. This delay is caused due to the inductor L.